Hello everybody, my name is Jannik Dreier, and I would like to present our work on the automatic generation of sources, lemmas, and Tamarin. As you all know, security protocol design is a very critical task, but at the same time very error-prone, as we have seen illustrated by many attacks. For example, on TLS there have been freak and logjam attacks, on Wi-Fi there were crack attacks recently. And one of the approaches that we could use in order to improve confidence in the cryptographic protocols is the use of formal methods. The idea is that we want to prove the absence of attacks in a formal model under some assumptions, or if this fails, we can identify weaknesses and correct them. To help us in these tasks, there have been many tools that have been developed, for example, ProVerif, Tamarin, AKIS, DeepSec, Avispa, SkySer, and so on. So this goes on for quite some time. But fundamentally, all these tools have a problem, which is that they need to make a trade-off between automation and completeness. In the sense that if they are highly automated, usually they have more problems with more complicated case studies, and vice versa. If they can handle very complicated case studies, usually they require more user interaction. Tamarin is one of the most popular verification tools in the symbolic model. It has many interesting features. It supports induction, loops, and mutable state. It has been used successfully for many large-scale case studies, for example 5G AKA, TLS 1.3, WPA2, the EMV payment protocol, and so on. Its security protocol model is based on multi-set rewriting. We'll see some examples later on. And it uses equational theories to model algebraic properties of cryptographic primitives. Internally, Tamarin uses constraint solving to analyze an unbounded number of sessions of the protocol. Something which is very interesting about Tamarin is that it both has an interactive and an automatic mode. The interactive mode is a web interface which looks like this here on the top right, and it allows the user to inspect and direct proof search, which gives the flexibility required for complex case studies and allows the user to fine-tune the models and the proof strategies. On the downside, Tamarin has an automatic mode, but it's not as automatic as, for example, ProVerif, as it may fail even on relatively simple examples. And one of the main reasons it fails is partial deconstructions. I'll explain what partial deconstructions are in a minute, but the main contribution of our paper is to automatically handle these partial deconstructions in most cases. So after this introduction, I explain what partial deconstructions are all about, and then I present the algorithm before talking about our implementation and the experimental evaluation. So what are partial deconstructions about? Consider a small toy example protocol between an initiator and the responder. Now this protocol only has two messages. So first of all, the initiator sends a message to the responder which contains a request tag, the identity of the initiator, and the nonce, and everything is encrypted using the public key of the responder. And the responder will reply to this using a message containing a reply tag and the nonce that he received, and this is encrypted using the public key of the initiator. Now, as I said, Tamarin uses multi-set rewrite rules to model protocols. So we could, for example, model the responder using the following rule. Everything here that's on the left-hand side of the arrow is called the premises, so everything we need in order to execute the rule. Everything on the right-hand side of the arrow is what's produced by the rule, and on the arrow we can add annotations that are used to specify security properties or intermediate lemmas. Here, for example, for the responder, so the responder will wait for an input of a message which is the asymmetric encryption of three values, the request tag, the identity of the initiator, and some nonce, everything encrypted using the public key associated to its private long-term key. These other two facts here are used to look up the long-term key of the responder and the public key of the initiator, which is necessary for the output, which is the responder's answer, so the encryption of the reply tag and the nonce using the public key of the initiator. Now, if I specify the other rules in this model, so I have to add a rule for the initiator and rules to generate the public and long-term keys. But if I do all that and I specify a simple security property, for example, the secrecy of the nonce, then it turns out that for this example it fails because Tamarin encounters partial deconstruction and the proof loops. So it does simply not terminate. Now, what are partial deconstructions and why are they a problem? So Tamarin internally pre-computes all possible origins, they are called sources, of all protocol and intruder facts. And this can stop in an incomplete stage, which is called a partial deconstruction, if Tamarin lacks sufficient information about the origins of some facts. Here on the right hand side you can see a screenshot from the interactive mode where you can see the raw sources, where we have a certain number of partial deconstructions, and then the refined sources where all deconstructions are complete. So how do we get to a situation where all the deconstructions are complete? Well, essentially we have to help Tamarin by telling him where the problematic facts come from, and to do this we use a sources lemma. So this is a special type of lemma that we as a user have to write and add to our model. Now Tamarin then uses them to refine the sources, but Tamarin also needs to prove these lemmas correct. So that if we wrote a wrong lemma, this will not endanger the correctness of the following proofs. Let's go back to our toy example. Here's a partial deconstruction that Tamarin encounters on this model. So in Tamarin, executions are represented using graphs, where each node of the graph is an instance of one of the rules of our model. So for example, here at the top we have an instance of our responder rule, which has here in the middle the input of the message from the initiator, and here on the top left we have the output it produces, and here on the other top facts are the two keys that we need for the rule. And now what happens in the pre-computation is that actually Tamarin started from this rule at the bottom. So Tamarin wanted to compute all possibilities for the intruder to have a term which is of the form second of T1. Now Tamarin computes all these things by backward search. So he started to look at all the rules and tried to extract values of these forms from all outputs. Now it turns out that here this rule doesn't output, and Tamarin said, if I had the right key, I could decrypt this value and extract the second value of the pair, which is the value x7. And here Tamarin stopped because x7 is a variable, and he does this could be of the form second of T1 or not, and so Tamarin does not know what to do, and he stops. So in order to resume, so the problematic value is the variable x7 here, and it comes from this input here at the top. As a human, if we look at the situation, we will say that, well, actually this value x7, it cannot be of any form, even though it's a variable, because we know that either it's the message sent by the initiator, and then we know it's the nonce therefore generated by the initiator, or it's some message constructed by the intruder, if the intruder was to mess with the message sent by the protocol. So we have to somehow specify this as a lemma, as a sources lemma, and for this to work, we need to first of all add annotations to our protocol rules. So first of all, we need to annotate the initiator rule with the message that is output. So here is the initiator rule, and I added the annotation of the name I here, which contains the message that is output. And for the responder rule, I also add an annotation which contains the message that is input and the variable x, which caused the partial deconstruction. And then I can write a source lemma, which says what we intuitively knew. So here the lemma is called typing and has the annotation sources in order to tell Tamarin that it's a sources lemma. And it says that, well, for all variables x and all messages m and all time points I, if I have the responder rule here for the message m and the variable x at time point a, so these adds are here to specify time points, then there exists a time point j such that the initiator output the message m at this time point j and j was before I. Or, second case, the message was constructed by the intruder, meaning that there exists a time point j where the intruder knew the variable x and j was also before time point a. And if I add this to the theory and I run Tamarin, this will actually resolve all the partial deconstructions, and then I can prove the security property very easily. Now, if we think about this, this is in some sense a bit mechanical because we just have to identify all the possible messages that can lead to the input that caused the partial deconstruction. And this is what we try to generalize in our algorithm. So we try to automate the proof by generalizing this idea. So the main idea of our technique is that we will inspect all the raw sources generated by Tamarin, and for each partial deconstruction we will identify the variables and the facts that cause the partial deconstructions, as I showed on the example. This is relatively simple because the variable is always like the second to last value in the graph, and the facts we can identify them just by looking at which facts contain this variable in question. And then we have to somehow identify the rules that produce the matching the conclusions. Now in this example it was very straightforward because there was only one other message. In general it's a bit more complicated, and I'll explain this in a second. And once we have identified all these rules, we can add the annotations. So we will add an annotation to the rule that caused the partial deconstruction, and to annotation to each rule that produced a matching conclusion. And once we have all the annotation, we can generate the source lemma and add it to the theory and ask Tamarin to continue using this lemma. Here note again that, as I said, Tamarin will verify the correctness of a generated lemma. So even if we were to generate an incorrect lemma, Tamarin will alert us. But we actually proved on paper that the lemmas we generate are correct under some reasonable assumptions. So we limited ourselves, for example, to a subterm convergent equational theory. But our approach might still work if these assumptions are not met. We are just not sure. So how do we identify matching conclusions? Well, as I said, in some sense we have to identify which outputs can match the inputs that causes the problem. The first idea was just to say, well, let's look at all outputs, all inputs, and try to unify. And this actually turns out to be insufficient because the intruder can mess with pairs, for example. So consider an example where we had an input of a pair of two encryptions and two outputs which are just simple encryptions. Here the unifications between the input and both outputs fail, but the intruder can easily compose outputs to generate an input. So here we need to do something. And our solution was to concentrate our unifications on what we call protected subterms. The idea is that a protected subterm is a subterm whose set symbol is not a pair or an AC symbol. So morally, it's an encryption, a signature, some kind of cryptographic object that the intruder cannot manipulate. And this allows us to abstract away pairs, and then we can identify matching conclusions by extracting what we call the deepest protected subterms containing the variable causing the partial deconstructions for the input facts in the raw source, and then we can extract all protected subterms from all other conclusions and try to unify these protected subterms. And if we have a pair of protected subterms that unify, we have a match, and we add the annotations and add a case to our lemma. So this is the high-level idea of our algorithm. Let's have a look at the practical results. So we implemented our algorithm in Tamarin, and we tried numerous examples, first of all from the SPORE library of cryptographic protocols. Now the SPORE library contains many classical examples, and we coded a lot of those, and it turned out that many of them actually had partial deconstructions. But for all cases where we had partial deconstructions, our algorithm was able to resolve them fully automatically, which means that it generated a lemma, and Tamarin was able to prove that the lemma is correct. And then we also checked whether this was sufficient to have, in some sense, full automation by specifying basic security properties like authentication and secrecy, and checking whether these lemmas were automatic. And it turns out that this was the case for all the examples here. So this was very nice, but these examples are relatively simple. So we ask ourselves, how are we doing with respect to more complicated examples? And to find more complicated examples, we took all examples from the Tamarin repository that contains partial deconstructions. And we removed all the manually written sources lemmas from these files, and then we ran our algorithm on it. And it turns out that for most of the examples, again, we were able to resolve the partial deconstruction and prove our sources lemma correct. Still, not all other lemmas in these examples became fully automatic. In some cases, you still need intermediate lemmas or some fine-tuning of the proof search. However, when our algorithm worked, it turned out that the verification time were more or less the same. So it doesn't seem that our algorithm adds a lot of overhead. Now there were 3 cases in which our algorithm actually failed. The first example was an example where we generated a source lemma, but Tamarin fails to prove it. So the proof simply doesn't terminate. So we expect the lemma to be correct, but Tamarin cannot verify it. This is something which can happen on complicated examples, obviously. And then we had 2 other classes of examples. Here for 5G aka, for example, the partial deconstructions do not stem from messages but from state facts, and they are currently not handled by our algorithm. And in the last case, the algorithm failed because these examples contained more complicated equational theories, so theories that are not subterm convergent or contain AC symbols. However, the results were quite encouraging overall. For all examples from SPORE, we were successful. Most examples from Tamarin, we were successful, and we had similar verification times. And yeah, we only had 3 cases of failure, essentially. So to conclude, the automation in Tamarin often fails because of partial deconstructions. We developed and implemented a new algorithm that automatically generates sources lemmas to remove these partial deconstructions. We proved the correctness of the generated lemma on paper. It turns out that our algorithm works well in practice. We tested it on many examples, and many of them become fully or at least partly automatic. This new feature is available in 1.6, and as future work we would actually handle more general equational theories. So this is one of the cases where we currently fail, or the second case we would like to handle partial deconstructions stemming from state facts, and this is actually currently work in progress. So if you have any questions, don't hesitate to contact me or the other authors, and check out the new Tamarin version and all the case studies which are available at the Tamarin webpage at tamarin-prover.github.io.